Hello again. We're going to do the second part of this. It's the same PowerPoint now, but we're going to look at what is. I mean, it's a trickier thing. Certainly, it's only ever been on the specimen paper, so it's possible that it could be on. But as long as you could do the stuff from last lesson, then it's likely that that should get you through any question about retaining walls and dams. Anyway, here's the formula from last lesson. So F equals rho HAG. We learn that rho is density, probably get given it. A is the area, so hopefully we know how to measure that. We ignore the height of the dam. It's the height of the water and the width of the water, all that's in contact with the dam. G is 9.81, and H we put as half the height of the water. So that's important to remember. You can easily forget that by the time of the exam. So that's the key thing to remember. H is half of the height. So if I go to the exam question here, we put for part two, F equals rho GAH, and H would have been 3 meters. Okay, so that's giving us, as I said, at the top of the dam, the hydrostatic force is very, very small, going up to 0, and then the bottom of the dam is very, very large. So really, we're giving an average hydrostatic thrust. But if we look at where forces appear to act from, which is what we'd need if we got a question about turning effects, then we need to look at this bit of theory, which is center of pressure. So if you have water on one side of a dam and the dam has this structure, you can't imagine a scenario where it's going to turn and the dam will just fall over. More likely it will buckle with holes in it. But if we look at this, a retaining wall, which is something, maybe not in huge dams, but you certainly could have something just holding some water back. That wall could turn, if you imagine the very bottom of it is a pivot, so the wall could turn clockwise there. So it could just, like the hands of a clock, just going from 12 o'clock to 3 o'clock, it could just fall right down if that water pressure was too much. So that is a turning effect. That water could have a turning effect on the retaining wall. So that means that we need to look at the maths of moments, which we did earlier in the year. So this is how we apply moments to retaining walls. So going back here, we have to decide where that moment would work from. And if you take the water as a triangle, which is what we do here, now you don't need to worry about why it's a triangle, but essentially, if we turn it into vectors and we have a larger force at the bottom, then we can take the total of the forces acting as a triangle. Then to find the center of that triangle, they call it the centroid, and it isn't halfway up. So from one corner to the middle of a side, from another corner to the middle of a side, and then the same again, and where those three lines cross, that's called the centroid. Okay, and there's defined at the bottom of the page. So, if we have the triangle upright, you can see the centroid is 2/3 of the way down that triangle. So when we're working on hydrostatic thrust, we treat H as halfway down, or even halfway up, same thing. But for moments, we need it to act from the centroid, which is 2/3 of the way down. Okay, so looking at this question, if you had worked out 9 part 2, then you would have the hydrostatic thrust. If they then had a follow-on question where they asked you for the turning effect or the moment, then you would just write down the formula for moments, which is moment equals force times perpendicular distance from the pivot. Okay, so you would write moment equals F times D. So the force is what you've just worked out. That's the hydrostatic thrust. That is the force. But D, distance from the pivot, has to be 2/3 of the way down. So the distance from the pivot, we're looking at 2/3 of the way down, would be 4 meters down. But from the pivot, which is at the bottom, it's actually 2 meters up. So all you're doing to work out the moment is taking the hydrostatic thrust, which you've worked out, and multiplying it by the distance from the pivot, which is 2 meters in this case. Okay, because the centroid, we would draw it as a vector triangle. We'd find the centroid, which would be here. So there, from there to the pivot, because that's where it would turn if it fell from 12 o'clock to 3 o'clock, that's 2 meters up from the pivot. Okay, so if there was a 9-part 3 and it asked for calculate the turning effect, then you would take your answer, that gives you your force. You'd write the equation moment equals force times distance from the pivot. You would then give your answer to part 2 as the force, and the distance would be 2 meters. For this one, same again, the hydrostatic thrust you've worked out. So then to work out the turning effect, you would write moment equals force times distance. Force is what you've just worked out, and distance would be 1/3 up from the pivot. So 3 1/3 meters up. Okay? So while it seems like a whole more complicated thing, essentially all you're doing is timesing your calculated force by one distance. Remembering that it's 1/3 of the way up, 2/3 of the way down, and remembering that when you work out the hydrostatic thrust, it's halfway down. That's the tricky bit. That's what you've got to try and note down and make stand out. Okay, so here's the question for today. So you have a retaining wall with water on both sides. We've got 4 meters of fresh water and 1.5 meters of seawater. So straight away, I'm spotting that they're going to have different densities. I mentioned that seawater is more dense than fresh water. And you can see that up the top there. We're using 1,000 for fresh water, but 1,030 for seawater. Now it's a 10-meter wide retaining wall. When we work out the area, it's the area of the water in contact with the wall. So the area of the fresh water is going to be 4 by 10, and the area of the seawater is going to be 1.5 by 10. Densities are different for either side. G is the same, it's 9.81. So when you're working out your hydrostatic thrust, you use the same H as last lesson, which is halfway down. So on the left, you'd use 2 meters. On the right, you'd use 0.75 meters. Okay, because we're working out hydrostatic thrust, the force. And when you work out the force, you use halfway down. So if you do the first part of this, which would be to work out the force or hydrostatic thrust on the left, and then work out the hydrostatic thrust on the right. Okay, you should have 2 answers in newtons. Hydrostatic thrust on the left and hydrostatic thrust on the right. Once you've done that, you can then work out the turning effect from both sides. So if you have your hydrostatic thrust on the left for fresh water, F equals rho G A H. There's your answer in newtons. Underneath that, write moment equals force times distance. For force, you use the hydrostatic thrust that you've just worked out on the left. And for distance, you use 1/3 of the way up. So the distance from the pivot is going to be 1 1/3 meters, 1.33. And that will give you a moment, and that will be a clockwise moment. The fresh water is trying to turn the wall from 12 o'clock to 3 o'clock. Once you've done that, underline that answer, that's your clockwise moment. Now we look at the seawater. Do the same again. Work out the hydrostatic thrust, F equals rho G A H. Once you've got that, that's your answer in newtons. Underneath that, write moment equals force times distance. The force is what you've just worked out as the hydrostatic thrust. And the distance is the perpendicular distance from the pivot to the centroid. which is a third of the way up, 0.5 meters. Okay, now you should have a clockwise moment and now an anti-clockwise moment. The seawater is trying to turn it from 12 o'clock to 9 o'clock. That's an anti-clockwise moment. So those are both in Newton meters, force times distance. So then to get the resultant turning moment, you would just subtract the anti-clockwise moment from the clockwise moment, and that will give you a resultant turning moment. That is a vector, so we need to give the direction. So your resultant turning moment would be a numerical answer in Newton meters with clockwise written on it as well. So please send me your answer to this one and any questions you might have. I'll support you individually. So hopefully you can get to a point where you write down what I've told you to write down. I would split your piece of paper. I would have fresh water on the left, seawater on the right. You write your first formula, F equals rho g AH for fresh water, and then second formula, moment equals force times distance. Same on the right-hand side, and then it's just a case of taking one from the other. Okay, so please email me with any questions, and that's all for today. So just this one question. And as I've said, let me remind you that while this could crop up, it hasn't really, but it's a good way to go over moments and have a bit more practice on that equation as well. Okay, take care.